Okay, so thank you everyone for being here, and thank you for thanks also to the audience for being connected. We keep moving forward in this series of seminars in the context of the Robotics Better Life initiative. So we basically one of the speakers that we wanted to invite was Russ Drake. Russ Drake from MIT. Russ mentioned us that Tobia, one of his PhD students, was actually in Italy, and he might have presented one of his latest work. And it's my great pleasure to introduce Tobia, who is a PhD candidate at the Massachusetts Institute of Technology, and that he will be presenting motion planning around obstacles with convex optimization. So thank you very much, Tobia, for being here, and the stage is yours.
Thank you very much. So good morning, everyone. Yes, my name is Tobia Marcucci, and the title of my talk today is Motion Planning Around Obstacles with Convex Optimization. We have chosen this title to be a little provocative, I hope, in the sense that motion planning around obstacles is typically seen as almost the textbook or stereotypical non-convex optimization problem. But the goal of this presentation today will be to show that practical convex optimization, convex optimization problems that can be solved efficiently and fast can actually solve non-trivial, actually quite complex motion planning problems for robots moving in environments with obstacles. So this is the outline of the presentation today. I will start with some motivation problems coming from robotics, like robotics, UAVs, and robot manipulation. Then I will move to the mathematical framework that underlies our motion planning algorithm. Then I will go a little more in the details of how we actually solve these convex optimization problems and more like the mathematical details of the motion planner. Then I will move to experimental results and conclusions. And please feel free to stop me anytime if you have questions, or I don't know if there is a set time at the end. So the talk today will be about motion planning problems, or more in general, I would say decision-making problems involving discrete and continuous decisions. In my lab, we have been working on this kind of problems for years, at this point, almost 10 years. And I will start with a few examples of how this mix of discrete and continuous decision-making arises in robotics. At the time of the DARPA Robotic Challenge, one of the key problems for moving the Atlas robot around was footstep planning. In the footstep planning problem, you want to move the robot from point A to point B. With the vision system, the robot scans the environment and can find a collection of safe convex patches on the ground where it's safe to place the feet. And the goal is to decide how to, what's the optimal sequence of footsteps to reach the goal. Clearly, this problem has a discrete nature that is kind of obvious. You need to select the sequence of patches that you want to place your feet on, but at the same time, it has a continuous nature because the positioning and the orientation of the feet is a continuous decision variable. And these two components of the problem, the discrete and the continuous, are coupled together in an inseparable way, in the sense that you cannot, for example, solve for the discrete part independently of the continuous, and vice versa. If you were to solve for the discrete part, maybe you would end up with a sequence of regions on the ground that are not kinematically feasible, or things like this. A different problem in robotics is motion planning, for example, for UAVs. But I would say that the underlying structure is pretty similar. For example, if you have a drone flying around obstacles, you might have discrete decisions of the form. If I have a tree in front of me, do I go right? Do I go left? Do I take the door or the window to go inside the building? And then you also have continuous decision making of the form. What's the shape of my trajectory within this convex, piece of space? And similar problems of this form, again, arise, for example, in robot manipulation. In warehouses, you have robot arms moving objects between shelves. You need to decide how to arrange the objects. You need to decide, for example, if you have multiple robot arms, how these will interact in a discrete way. But of course, you also have the continuous component that is the actual movement of the robot. So what's the state of the art in merging these two aspects of motion planning? Continuous motion planning and discrete motion planning. I guess many of you are familiar with the newest results from Boston Dynamics. Well, actually, these are not even new, but they are still extremely impressive to me. How does the Atlas humanoid work in a few words? How do they do this motion planning? Offline, they generate a library of template behaviors. A template behavior can be, for example, a jump, a backflip, running. And then online, they run a convex optimization to merge these behaviors. So for example, if you have in front of you a parkour environment, the engineers decide a sequence of behaviors that need to be adopted to go through this parkour environment, and the robot on the flies using the sensor adapts the offline computed behaviors. So what's the issue with this? The biggest issue is that the discrete sequence of behaviors is designed by the engineers. So the robot is not able to perceive the environment and decide how to sequence the behaviors. So if, for example, in this, in this kind of stepping stone scenario, one of these ramps would be missing, the robot would just fall, would not realize that, would not react to structural changes in the environment that it perceives. So summing up, we have a multitude of practically very important problems in robotics that involve this mix of continuous and discrete decision making that is also very challenging and very interesting from a mathematical point of view. Again, these problems have this discrete skeleton. Typically, you have this underlying or higher level discrete decision making, but then you need to fill the details of the robot dynamics. And this structure is shared by the various problems I showed you so far. The goal of my research in the last years, and the goal of this presentation today, has been to develop a simple mathematical framework that allows us to formally reason about these kind of problems. And actually, of course, as many of us, improving on state-of-the-art algorithms for robots to navigate in their environment. And the proposal that we came up with after, at this point, 3 or 4 years of research has been this framework of finding shortest paths in graphs of convex sets. And I will now present what this mathematical problem is and how it can model the kind of problems I just described. So I guess many of you are familiar from operation research classes or network classes with the shortest path problem. We are given a directed graph. We want to move from the source to the target, and we can move along the edges in the graph. And the goal is to find a path that connects the source to the target, and that these paths must have minimum length, where the length of the path is the sum of the length of each edges, and the length of an edge is a constant. We consider the generalization of the shortest path problem depicted on the right. So to each vertex in the graph, we pair a convex set. And the position of a vertex is not fixed in space anymore, but the vertex is allowed to move within the corresponding convex set. Again, the goal is to find the shortest path from the source to the target sets, in this case. And the problem is mixed, discrete, and continuous. Discrete because you need to find a path through a graph. Continuous because along this path, you are allowed to optimize the positioning of the points that you're going to visit on these kind of islands. I'll be more clear on the problem formulation in a second, but my goal today would be twofold. The first would be to convince you that this is a very versatile problem statement, in the sense that many interesting problems, from control of hybrid systems to motion planning, can be seen to be special cases of a problem of this form. And the second goal would be that this problem is efficiently solvable. Formally, this problem is NP-hard, so we do not have an efficient algorithm in the theoretical computer science sense, but we have something that works really well in practice. And I would almost say that almost any problem that you can put in this form we can tackle at the highest level of generality, and we can solve efficiently. So this can also work as a modeling framework, as a way, as an interface for you to give us a problem that we can solve very efficiently. In particular, we describe how this problem can be formulated as a mixed integer program, but the important part is that this mixed integer program will have a very tight convex relaxation. So most of the problems that we encounter in practice can be solved through a single convex optimization. And of course, you understand that the goal would be to take a motion planning problem and put it in that form so that we can use our machine. So let me be a little more precise on the problem statement. We are given a directed graph. The vertices are capital V and the edges are capital E. For each vertex in the graph, we have a convex set and a point contained in a convex set that represent the position of the vertex. We have seen in the classical shortest path problem, the length of an edge is a constant. Now it's not a constant anymore, it's a convex function. In particular, of the 2 points that the edge connects. So for example, the length of the edge that goes from the vertex U to the vertex V is a convex function of the position of vertex U and the position of vertex V. And we assume this function to be non-negative. A path in a graph is defined as it's normally defined. It's a sequence of vertices in the graph that connects the starting vertex, the source, to the target, and you are allowed only to travel along the edges in the graph. With this notation, the problem we study today, the shortest path problem in graphs of convex sets, can be formulated like this. We look for a path, pi, that must be a valid path that connects the source to the target. And along the path pi, we want to optimize also the position of the vertices that we encounter. And the cost function is the total length of the path, defined as the sum of the convex edge lengths. Any question on the problem formulation? So we have this mix of discrete, because we are looking for a path, and continuous, because we are optimizing continuous decision variables along the way.
Sorry, so
yes.
The decision variables are phi and x.
Yes. It's then I will formulate it as a more tractable optimization problem, but here we are looking for a path, and along the path we want also to optimize the positioning of the vertices. Okay, so a couple of comments on this problem formulation. It can be generalized a bit in the sense that we can have other sorts of constraints in the problem framework I just described. For example, we can add constraints, convex constraints on the relative position of the vertices that are linked by an edge. For example, we can ask this point and this point over here to be paired by a convex constraint. For example, the dynamics of a linear dynamical system is a convex constraint. We can also add costs on the vertices. In a sense, we can ask, okay, if you want to traverse this vertex, you need to pay a certain cost depending on the positioning of that vertex. It's easily seen that they fit as special cases to the problem I just described. I just mentioned it because I will use them in a second. As I said, the problem is hard theoretically, but in practical, most of the instances we find in practice can be solved efficiently. It's NP hard. And let me also mention that similar problems have been discussed previously in the operations research literature, but the numerical techniques they presented, they are not even close to the kind of problems we will tackle today. Previous methods were limited to 2 or 3D problems. We tackled problems easily in hundreds of dimensions. As I mentioned, the motion planning algorithm we propose is based on trying to reformulate the design of a continuous trajectory into a shortest path problem in graphs of convex sets. So let me briefly discuss how we can do this in a simple case. And let's say that we want to design a continuous curve that connects the starting point to the target point on the top right. And we want in particular the shortest curve that avoids the obstacles in red. The first step that we do is to decompose the free space in convex regions. This is not an easy problem, but there are good algorithms for it. It's actually a hard problem itself. but this is actually a standard starting point for many path planning algorithms in robotics. So let me assume we have this decomposition. Then there is a natural graph that we can construct from a convex decomposition of the free space, that is the adjacency graph of the regions. We have a starting point, a starting vertex that is paired with the starting point, a goal vertex that is paired with the ending point, and then we have a vertex per region. And we draw an edge between two regions, for example, region 2 and region 3, if these two regions intersect. Region 2 does not intersect with region 5, so we don't have an edge. So this is the adjacency graph and will be the graph underlying our shortest path problem. What are the continuous decision variables in this problem? The points that parameterize the trajectory. Let's say for simplicity that we want to parameterize a piecewise linear trajectory, then to each region we assign a starting point and an ending point. Then we construct a shortest path problem in graphs of convex sets, where we can ask things of the form, okay, if you want to transition from region 1 to region 2, you'd better have that the final point in region 1 coincides with the starting point in region 2, and things like this. And in the formulation of this problem, then we pair a path through the discrete graph to a sequence of regions that we want to traverse. And then we can have convex costs. For example, we can ask that traversing a certain region, you pay the price of how long is the trajectory segment in that region. So you are actually formulating the minimum length problem in this case. This is the simplest kind of example we can come up with. This approach naturally generalizes to polynomial curves using Bezier polynomials. We can have a cost and constraints on the duration of the trajectory, the velocity. We can ask the trajectory to be differentiable arbitrarily many times. Currently, we are still struggling with acceleration constraints for some mathematical reasons, but to give you an idea, this framework is pretty general and we can design pretty interesting trajectories using it. Any question on this? Even on from no? Okay.
I keep monitoring the questions.
Okay, okay, good, thank you. Because I don't have a window here.
Don't worry.
Okay, let me then spend a word on how we actually solve this optimization problem in practice. I wrote down before an optimization problem, but it wasn't really something that you can handle to an optimization, standard convex optimization solver. In fact, it was not even convex. So as we said, the problem is hard. So there is no hope for an algorithm that solves all the instances in polynomial time. What we came up with is a very tight convex approximation of the problem. So you should think of this as another problem that approximates tightly the original problem from below, the original cost functional from below. And this will actually be an exact mixed integer formulation, but we don't care too much for today. How do we construct this convex relaxation? We start from the classical integer programming of the shortest path problem, the one with constant edge lengths. In this problem, the decision variables, we have a decision variable per edge, ye, and these are like flow variables. You can think of these as the amount of flow that is channeled in each of the edges of the graph. These variables take value that is either 0 or 1, with a value of 1 in case the edge E is along the shortest path. So these are the variables in the classical linear integer programming formulation of the shortest path problem. This is somehow an ideal starting point because this problem has some very nice algebraic structure that is such that its convex relaxation is exact, meaning that if instead of asking the variables to be binary, you just allow them to be between 0 and 1. So instead of either 0 and 1, you allow them to be either 0 or between 0 and 1. You get a drastically simpler optimization problem. You get a linear program. And this linear program can be verified to be exact. In the sense, this is naturally an under approximation that is exact. So this is like the ideal starting point in integer programming. We can extend this problem formulation naturally to our graph of convex set scenario. We introduce the continuous variables, and we substitute the constant edge lengths with our convex functions. Then we need some tricks and some manipulation to restate this as a an optimization problem with bilinear equality constraints, where we have some variables in a convex sets, some other variables in a convex sets, but then we need to keep track of the outer product of these variables. Here I'm being a bit high level because going into very details would be a bit tedious. So the whole mathematical effort has been in the design of a convex relaxation that is actually very tight and very efficiently computable of non-convex constraints of this form. I can give you more details offline, but let me just give you these 1, 2, 3 points for now. So about this convex relaxation is very tight because we started from something that is some way ideal, the best formulation you could hope for the original shortest path problem. We extended it to our problem, and we got this only issue that was this bilinearity between these variables, the variable parameterizing the path and the continuous decision variable. So the only gap, let's say, is due to our convex relaxation, which actually is theoretically seen to be a very good approximation. The problem is compact. It has very few decision variables and constraints, and is typically a linear or a second-order program that can be solved efficiently with common optimization softwares. So how do we actually solve this problem? As I said, it can be seen that it's a mixed integer program, so we could call complicated a branch and bound algorithm, but this is not really what we do because the convex relaxation is so tight that in all the problems we encounter in practice, it's sufficient to solve the convex relaxation and then round the optimal solution. From the convex relaxation, we will get indicator variables on the edges that are not necessarily 0 or 1. These variables are naturally interpreted as probabilities. They kind of induce a probability distribution over the graph. So a natural approach to round a problem, the solution of the convex relaxation is to run some, for example, a randomized depth first search. Since this takes almost 0 time, we can run it 100 times and take the best. It takes like 10 to the minus 5 seconds, try to round a small graph like this. So the idea is that we solve the convex relaxation, and then we use a randomized rounding many times, and we pick the best. And it typically takes a very small amount of time. A few advantages of this approach is that it automatically provides bounds because the convex relaxation gives you a lower bound. The rounding gives you an upper bound on the cost, so you sandwich the global optimum. It's very cheap. It's basically a convex optimization, and it does not require expensive and complex mixed integer solvers. So for the last 10 minutes, I'll go to numerical results and experimental results. Let me mention that this is implemented in Drake, the software we developed in our lab together with the Toyota Research Institute. The implementation is very mature and documented. It's in C++, so it's also effective. If you want to give it a try, let me know. We'll try. And let me start the numerical example with almost a totally example that is, again, a bit provocative. How do we find the path through a maze from this point to that point and down? If you come from computer science, you say, well, it's trivial. It's a graph search. Depth first runs in, I think, n log n, when n is how many cells you have. But this is not really the kind of problems we want to solve because we are not only interested in finding a path, a discrete path through the graph, but sometimes we have like differentiability constraints. If it's a UAV that flies through this environment, for example, you want the trajectory to be differentiable 4 times. So not any turn can be taken at a certain speed, or maybe it requires too much thrust. We chose this problem exactly because we think it breaks most of the planning algorithms we have in robotics. Local optimization here is hopeless. IP opt or non-convex optimization, too many local minimals. Sampling base, you would basically have to read the whole thing before finding a path. And also this path would not be differentiable. And previous mixed integer approaches would have an enormous number of variables, in particular squared of the number of cells in the maze. So we would have millions of decision variables. Our formulation has a number of decision variables that is scaled linearly with the number of cells. We can easily find the minimum distance path through the graph. We can find the minimum time. Assume here you have a robot that needs to go there as fast as possible, but it has velocity constraints, and you want the trajectory, for example, to be twice differentiable. this is something we can solve very easily. Importantly, for both these problems that you see here, for both these trajectories, the convex relaxation was exact, meaning that you solve the convex optimization, the graph that you constructed end up having directly 0, 1 variables out of the convex relaxation, meaning that the solution we have found is guaranteed mathematically to be the global minimum. Let me be precise and say that for the minimum distance problem, this is more or less a sanity check, because this problem could be solved again in polynomial time with some magic. So it's not impressive that convex optimization can solve this exactly. But for the minimum time problem, I think this is a nice way of our algorithm merging continuous and discrete decision making, because I don't know any other algorithm that can solve, can design a path like that. We tried the motion planner on the UAVs, just in a simple simulation environment. We tested on 100 random buildings of this form. In this case, the decomposition of the free space can be done exactly because we have polygonal obstacles. And we planned the trajectories in 3D for this UAV, and we used the differential flatness to reconstruct the orientation and the thrust of the UAV. So we need to plan trajectories that are highly differential. These are the histograms of the results. In the first histogram, we compare the optimal cost of the rounded solution that we get compared to the global minimum. So on 95% of the buildings, through a single convex optimization, we find the global minimum. And even in the worst case, the solution we found is only 3% worse than the global minimum. So basically, we solved the problem statistically, not mathematically, but statistically. And this is the second histogram shows the gap that is certified by design by our method, because we have a lower bound from the convex relaxation, an upper bound from the rounding. We can compare these two numbers and give an estimate, a conservative estimate of how far we are from the global minimum. And you see that 45% of the times, not only our planner finds the global minimum, but also certifies it by design. And even in the worst case, it says, well, you might be 20% away from the global minimum. And actually, we were in the global minimum most of the times. And let me mention that problems of this form were previously tackled with very complex mixed integer semi-definite programming and took hours. Now we can solve these in 0.1 seconds kind of regime. We have compared our algorithm with sampling-based motion planners that are typically used by many companies, actually. This is the PRM algorithm in action. Many of you are familiar with it, I imagine. You construct a dense sampling of the joint space of the robot, in this case, a 7-dimensional space. And then at runtime, you're given a starting point and an ending point, and you need to find a path through this discrete graph that you check offline to be collision-free. This method is known to give very, very bad trajectories. In fact, you see that the robot is doing a lot of nonsense here. What people typically do, and companies like Amazon and Toyota use this, they post-process the trajectory from the PRM method with a randomized shortcutting algorithm. And this gives drastically better trajectory, but can easily get stuck in local minima. Our method, on the other hand, this should be our method, can solve this problem much more efficiently, in particular to the global optimum, guaranteed, and doesn't get stuck in local minima. This is the comparison in numbers. On the left, you have the quality of the trajectories we designed. The lower, the better, and ours is the blue one. You say that the original PRM method is very bad. The PRM with shortcut improves the trajectory of the PRM, but our method gives better trajectories throughout the experiments. On the right, you have computation times. PRM is a discrete search in yellow. Discrete graph search runs a diced algorithm, so it should be very fast. And then you have the overhead of the PRM with shortcutting that makes it a bit slower at the price of having better trajectories. Our algorithm is even faster than the original PRM. Let me conclude by mentioning that now we are moving to much more complex motion planning problems. Here we have two KUKA arms that need not only to avoid collisions with the environment, but also with themselves. So here we are planning in 14 dimensions. Given the trajectory parameterization, this shortest path problem, I think, is in 180 dimensions, because we have multiple knot points of the trajectory that is parameterized as a polynomial that we need to optimize over. And you can imagine that the PRM method here has basically no chance of working. I've never seen a PRM method that goes beyond 8 or 10 dimensions. Our method still here is not, the trajectories are not optimal because of the approximate decomposition of the configuration space, but you can see that our method basically doesn't suffer dimensionality. It grows basically linearly in the complexity, in how many dimensions you have, as opposed to exponential. So I think this is very encouraging, and we are working in particular with Amazon, Toyota, and XI for implementing this kind of algorithms on real warehouses. So let me conclude. I hope that I convinced you that the shortest path problem in graphs of convex sets is a versatile optimization framework. More or less any problem that can be fit in that form can be solved efficiently. And in particular for motion planning problem, it reduces very often the complicated motion planning problem to a simple convex optimization, a linear or a second order problem. We are now working on extending the class of motion planning problem with support, acceleration constraints I mentioned, and other things like these, constraints, vision constraints and things like these, for example, for mobile platform with arms and vision. We are working on a customized optimization solver on the GPU. Eventually, we would like to have a standalone toolbox. You can just provide the sets and the edges and we solve your problem. And then we are also working on problems where you don't have the full graph memorized at the beginning of the motion, so you need kind of to explore and at the same time optimize the path. So it's kind of an online learning scenario. Let me conclude by thanking the co-authors of the two works I've presented today, Ras, Pablo, Jack, Mark, and Dave. And these are the two papers that I've presented. This is more like the theoretical mathematical one, and this is the application to robotics if you want to have a look. And thank you very much for listening.
Thank you very much, Tobia, for the nice presentation. Any questions from the audience?
I don't know. No, if people inside, if they have questions, they probably need to go.
Yeah. If people from the connected remotely questions, do not hesitate to raise your hand. Okay, so I actually.
No, I was saying probably.
I think that they hear us, right?
Could you hear us?
Yes. Okay, great. So I have a couple of questions, Tobia. So if you can get back to the approximation of the convex regions. So if I got it right, so do not hesitate that I was right here. So you basically assume that there is this decomposition, right?
Yes.
So, and I was wondering, what if you have redundancy? So, and you have different types of kinds of decompositions. How to pick up one and what is the effect?
What is the best?
What is the best? How to pick up and what is the effect on your method?
That's a very good question. So we have been working on this. Actually, there is a work. It was actually in the final slide, but I skipped it from a guy from our group that is working on optimal decomposition on these environments. It's a very hard problem. Finding even defining what's the optimal decomposition is hard. My experience is that for our algorithm, we would like to have regions that are not redundant in the sense, in particular, that they don't overlap. Overlapping might be dangerous. The bigger the regions, the worse the convex relaxation, slightly, not sensibly. Typically, it doesn't really matter too much if you invade a bit another region. It's not that sensitive, but if I were to pick between two, I would pick the one with the least overlap and also the least number of regions, because the size of the optimization problems is linear in the how many regions we have, and the computation times is polynomial in them. So less regions better. And it's a complicated trade-off. You have seen that at the end we had these motions that were not really optimal. This was because maybe an obstacle was like this in configuration space in 14 dimensions, and we ended up with a region that was very conservative. It might be that we can have more regions to have better trajectories, but then you pay in terms of computation times.
Okay, this is clear. The second question that I had was, it seems to me that you mentioned that you can impose velocity constraints on
the trajectory.
So basically, you inherit also stability constraints by doing this. So you can actually generate those velocities which are, because I mean, theoretically, the question that one might have is how to have stable trajectories.
That's a tough question. Let me be precise. We can have velocity constraints if you parameterize the trajectory with, I don't know, state variable x. We can have a constraint on x, and we can have a constraint on x dot.
Yes.
We cannot have coupling constraints.
Ah, okay. So you cannot have feedback.
We cannot handle continuous dynamics.
Ah, okay.
We can have discrete time dynamics in our setting because the relation between the current state and the state at the next time step,
okay,
it's a linear map, so it's a convex constraint. But differential constraints are hard, in particular because we don't want to fix a priori the timing of the trajectory. If we were to decide how fast we travel the trajectory a priori, that would be easy. But it's, I mean, you can convince yourself that deciding how much time you spend a priori in a convex set is not obvious. If, for example, the convex set is very, kind of tall, it's narrow and tall.
Yeah.
You don't want to say, I want to spend,
yeah.
So yes,
Okay,
that's an issue.
Yeah,
so yeah, it's very complicated, playing with the algebra of the things to understand what is convex, what is not convex.
Okay, I got it. Okay, so I don't know if there is any other question. No, and
I can ask one from here.
Yes.
Yeah. Ciao, Tobia. Very nice talk. Congratulations. Very, very interesting. The question is about the completeness. Once upon a time in planning problems, the completeness was important, and now it's less popular. But the question is, at some point you mentioned that you could prove that the solution to the maze problem, I think, was the optimal, meaning the global optimum, if I'm not mistaken. And that is astounding. That's a big result. So how do you guarantee that? And more generally, under what conditions can you say that if a solution exists, you will find it? Okay. Or especially in those classical tight problems where it might be very hard to find.
It's a very good point. Let me go back to and maybe the answer will not be completely satisfactory, in the sense that what I meant here is that a posteriori, when we have a trajectory, we can certify that it is globally optimal, because we solve the convex relaxation that gives us a lower bound on the optimal cost. If this convex relaxation has the binary variables that are already 0, 1, then we also have an upper bound that matches the lower bound, so we have sandwiched the global minimum between two equal values, and we have a certificate. We do not have a proof that our algorithm for any, for example, two-dimensional maze will always find the minimum distance path through a convex optimization. This is something, this problem is actually solvable in polynomial time using work back from the 70s, from Tomás Lozano Perez. Those people, they had these polynomial time algorithms for 2D environments with polyhedral obstacles, but our method is not proof that for any instance, so it's not complete in that sense. We could run, of course, the mixed integer solver. That would be complete, but would run in the worst case in exponential time. So it's an interesting research direction. We are working on it, on which kind of subproblems we actually do have a certificate that the convex relaxation will be tight, and it turns out to be harder than what we thought. But yeah, it's a very good point. It's complete with the potential issue of running in exponential time. With this work, we wanted to emphasize that most of the times a convex optimization that is polynomial time solvable is enough.
Okay, thank you. Thank you.
Thank you.
Silvia?
Yes, so thanks a lot for the presentation. And I was wondering, in the numerical result that presented, so once you reach a convex problem, it's easy to solve. But in practice, how did you solve it? Which I guess you were using a nonlinear optimizer. So which optimizer did you use?
So all the experiments here we used Mosaic, other solvers that solve. So yes, other solvers that solve this kind of optimization problems we end up with, these convex optimizations are Gurobi, and then basically any semi-definite programming solver with these are special cases of semi-definite programming. As I said, it's not ideal because these are proprietary solvers. They cost money. For example, now that we are working with companies, for them it's like an absurd amount of money, like $7,000 a year per core. We are speaking about. So we really want to have our own free convex optimization solver tailored to these kind of problems, because that would make the tools certainly more appealing for companies, because it could be free instead of relying on.
Also research institute, because for example, Mosaic is free for university, but it's not free for non-educational research institutes.
I imagine, yes.
So in our case, for example, we have the same problem with Mosaic, even if we're not a company.
Yeah, I think it's my goal for next year, coming up with a GPU solver for this GPU or GPU, depending on the availability.
Any other question? Yes, Stefano?
First of all, thank you very much for the presentation. I was wondering then how this would apply to the initial problem you mentioned about Footstep lines of the human robots. In that case, you could Footstep and consider these ones like kinematic feasibility and design feasibility. I was wondering how this problem is treated into the
Yes, I actually had to cut that part. I left the introductory slide, but they didn't have the numerical results. On those kind of problems, for example, let's say that you have a simple dynamical model, kinematic limits plus a second order dynamics, and you have like 30 stepping stones randomly generated in the environment. Our tests is that where previous methods would take tens of minutes, we are of the order of a second in those planning problems. So we are, I cannot do the math on the fly, like 600 times faster. And that was, this is really, and there is a geometrical reason, because the way they were writing the problem down before was basically, I would say, not ideal, actually like wrong, because the way they would write it before was still using these binary variables, but they would associate the footstep to a region with a fixed horizon in front of you. If you try to take the convex relaxation, the natural convex relaxation of something like this, the convex relaxation says moves anywhere in the convex hull of the stepping stones you have in front. So the robot will always go straight when you solve the convex relaxation. So the first information you get out of your optimization problem is the solution of the convex relaxation. Then you can do branch and bound and things. But the initial information is go straight to the goal independently of the environment. While our convex relaxation, having this underlying graph structure, is much more informative, and most of the time is actually exact.
Okay. Any other question? From the cloud, is there any question? Okay, so if there is no, let's thank Tobia.
Thank you.
Thank you very much, Tobia, and we'll move forward for the chat session.
Okay.
Yes, thank you all to those connected. Thank you.
Thank you.
Bye.
Thank you to the speaker.
Thank you.
Bye.
Goodbye.
Thank you. Thank you.